Good afternoon, everybody. Welcome to a cold but fun-filled afternoon at Chem 170 with your host, me, Dr. White. Happy February 1st. Yep, I just looked at the calendar. I have an electronic calendar right above here, clock calendar. It's the 1st of February, whatever that means. Although it's the 1st of February. All right, a couple important things. First of all, I always get, how should I say this, messed up when this semester starts on a Wednesday, not a first of the week Monday. And I did it this time, but it's something I can fix. And that's the date for test number 1, which originally is scheduled for next Wednesday. Sent out an email this morning, plus posted this announcement. There's a new date. Test number 1 will now be on Wednesday, the 15th of February this month. I do this so I don't have to rush to finish. I could push it, but that's not fair to you. And I always try and do things that will help students, not just to keep me on track with something I put in a syllabus. Now, the rest of the hold on one second, I get rid of that. The rest of the test dates should not change. And this usually happens. So remember, test 1 has been postponed by 1 week, and you should have all gotten an email to that effect. And put that in your calendar. Now, another thing, I'm going to do something a little differently. Normally on a lab Wednesday, which is labs are always on Wednesday, just like if we were face-to-face, I would lecture for 50 minutes, take a break, then we do the lab, and then you get out early. And in real life, face-to-face, if we're at ECC, I'd be lecturing for 50 minutes, and then afterward, we take a break, do the lab. When I say do the lab, what happens is if we were face-to-face, we go in what's called the dry lab room, which is a classroom right outside the lab. And I would do my introduction for about 20 minutes or so. And then you go in and I show you, and I'm watching you, so you don't get hurt. And also you have a good time doing the lab, because I'm there to help you know what to do. You do the lab and you'd be out in about an hour or so. But this morning, my SUV needed its oil change and all that. And the dealership I've been using for many, many years, Friendly Ford in Roselle, they actually pick up my car. They did that at 9 this morning, and they'll drop it off. And I asked them to drop it off after 2:30. So what I'm going to do, which is different, I'm going to do the lab first. Normally I do it second, so I can make sure I get that in. Then I'll lecture in either 2:30, or if they call, I may have to take the call to give them my credit card to pay for the work. And hopefully, there's nothing wrong. Actually, there's nothing wrong with my car, but it's an older SUV, and you never know. All right. First of all, any questions on test number 1, new date? All right. Like I said, normally we'll do the second, but today, because I don't know when they're going to drop off my car and call me, I'm going to do the lab first because I want to get that done. Now, if you go to D2L, you'll see assignment area. And if you click on, let me go and view student view. Again, this is what you would see. Click on assignments, and you'll see assignments you should be doing. Don't forget, hand in the signature sheet as a PDF file. Now, as someone asked to, I actually had a visitor last night to my office hour, thank you, but don't forget, I have office hour tonight from 6 to 7:15. If you have any questions, come on by, it's on Zoom. Now, you'll see here, melting point slab. And I have 2 documents. One is melting point lab, and it's Microsoft Word For those who don't have Microsoft Word, I also have it as a PDF file. Now, what you'll be doing is you have, and I'll explain it in a second, till next Wednesday to answer the questions in this lab and upload it as a single PDF file. Please do not upload JPEGs. Makes my life infinitely harder, which I don't need. I never need that. And I have two files, one a document, Word doc, the other PDF, different ways you can make a PDF file from today's lab. And you can also type in your answers in the Word doc. Or if you have the app to open up a PDF file, that's fine too. Now, if you have a scanner, use it. If you don't have a scanner, what I recommend you do on a piece of paper, write your answers for the lab. You do not have to write out the questions. I already know them, I have them. So you don't need to do that. And then I think everybody in my class, A, either has a cell phone or B, has access to a cell phone. And it's my experience, unless it's changed, I think all of you have cell phones, but if you don't, I'm sure you have access to it. And you can make a PDF file once you take a picture with your cell phone of each page of your answer. And then in this file, there's a way you can do it directly, or if you want, there's a nice app that I learned about a couple of years ago from one of my students in Chem 170 called CamScammer. Now, CamScammer, they have the free version and the paid version. Don't pay any money. You don't need all the extra bells and whistles. The free version works fine. And then you'll upload it to here. And if you have any problems doing that, let me know. All right, let's do lab number 1. All right, thumbs up, people. Even though I haven't done it, let me check. Do everybody see Chem 170 melting points on your screen? Thank you. This, like I said, just recently Zoom upgraded and put in, and I can see what I'm sharing. Before, I'd always have to have SAS. All right, today's lab deals with melting points. And I'm sure you've all seen, I don't have one, an ice cube. You put an ice cube in a glass and walk away for a couple hours. It's solid. When you come back, it's a liquid. It's melted. Now, inorganic molecules have a very sharp melting point. Organic molecules have a wider melting point. And a melting point is when a compound goes from a solid to a liquid. A melting point is when a compound goes from a solid to liquid. And almost all organic compounds have a much lower melting point than inorganic. And the question is, why? What's the reason for determining melting points? Well, there are two reasons organic chemists do this. It helps identify an unknown compound, organic compound. That's reason number 1. Melting points can identify unknown compounds. And it's also used to determine the purity of an organic compound. Is it all 100% that compound, or are there other things mixed in? So melting point helps organic chemists identify unknown organic compounds and also determine purity of an organic compound. Now, for my PhD thesis, well, that was a while ago, I created or synthesized, that's a better word, about 130 new compounds for my research. And most of them were solids. And each one I had to do a melting point and other things too for my thesis. And because the thesis was so important, I didn't do one, I didn't do two, I did three for each one to make sure they were correct. That was a lot of work, but it was worth it. Well, I got my PhD. But anyways, let's look at something important about a melting point. If you heat up a compound, organic compound, it starts out as a solid. And if you watch it, and the apparatus we do allows you to heat it slowly and watch it through a magnifying lens, and also know the temperature of that sample. At a certain point, and we call this the starting point, you'll see some liquid, or see really any liquid, like a little drop. Because initially you start out with a sample that's all solid. Now, after a while, you'll see the finish point or end point is when your sample is all solid, all liquid. So you'll have a range. Let's say you have compound X. Dr. White's being very creative, not. And you want to know the melting point. You take the sample, you start heating it, and at 100 degrees C, you see some liquid. That's the starting point. And then by the time when you get to 103, it's all liquid. And that's your end or finish point. So the melting point for compound X is 100 to 103. And that's how you determine melting points, by heating a sample and determining when you first see any liquid in the sample you're heating. That's the starting point, the first temperature, and the end point or finish point is when the sample is all liquid. Now, because in the different equipment, usually you have a very small, what's called capillary tube, and you want to put as little solid as needed. Because if you put too much in there, guess what? It's going to increase the end point. It's going to take longer to melt all that extra material. So when you put it in there, you put very little in there, just enough to see. All I can see is solid. I can see when any liquid is formed, and I can see when it's all liquid. So melting point, starting point, when you see any liquid in the sample when you're heating it, end point or finish point when the sample is all liquid. Now, in this lab, you'll be determining, first of all, if we were face-to-face, is to give you a practice doing melting points, which we can't do in Zoom. But, and also I've seen the different labs you use, computer labs don't do a good job. I know I've tried a couple. Oh, by the way, I forgot how many thousands of melting point in my life I've already done. But anyways, what you'll be doing is measuring the melting points of some known compounds, then some mixtures, and then an unknown. Now, why do I say that melting points are used to determine identity and purity? Well, it turns out you can go out in what we call the literature now on your website, any kind of search engine, you can find it, and you can find the melting point of certain compounds. And if you have a melting point of this certain, say 100, 103, you can find out what compounds are in that range, and it helps you narrow and identify it. That's how we use it. Now, in real life, if you're a rookie like you would be, and the way I wrote this lab is how the actual data students would get if you were doing it, your melting points are usually going to be lower than the what we call literature value. You never get one way higher unless you've done something really wrong, which doesn't happen. But most of the time, yours will be lower. So with that in mind, that helps you identify it. Now, the other concept that helps determine purity and also identity is called the colligative effect. And one thing I should mention, in this class, I keep lecture material and lab material separate. And that means there'll never be anything on a lab on my hourly exams. My hourly exams are just for my lectures, and the labs, the lab. I don't do lab quizzes. You're going to be writing up a lab, and I'll talk about that in a little while. Now, the colligative effect, if you forgot about it from your general chemistry, when you mix two things together, same with the same melting point, what happens is, even though they're same melting point, if they're separate things, colligative effect, the melting point of the mixture is always lower and wider melting point. The colligative effect of separate things with the same or even dissimilar is always lower and wider. So think about that. If you have a colligative effect, well, if I spell colligative wrong, let me know. I was always first down in a spelling bee. I still be today, but in math and science, I always won those competitions. So when you have the colligative effect, when you mix two different compounds, the melting point will be lower and it'll be wider. Interesting, in this weather, I always remember colligative effect also affects boiling points, and your antifreeze, which I'll talk about later in the semester, has water with another compound, which lowers the boiling point and the melting point of water of the antifreeze mixture, which is why it's good in this kind of weather in your radiator, so it won't freeze. So what are we going to do in this lab? What you'll do, and by the way, I'll let you do this on your own. Please watch this YouTube video, and especially about from 5 minutes 42 seconds to the end is the best place to watch it. Sorry about the blank paper. If you were in a lab, sometimes you have to pulverize it using a mortar and pestle, grind it up, and then you'll fill it in a capillary tube. Now, one quick trick. If this were a capillary tube and it's open top this end, here's my sample in a beaker or a bottle. You go like this, and there's crystals up here. How do you get it from here to the bottom here of your tube? You take it and tap it like this on a hard surface. And if it's dry, good crystals, it falls right to the bottom. That's a secret tip from a chemist who knows how to do that. And what you'll do is start heating it. You don't want to heat the sample too quickly because you'll blow right by the melting point and get higher values than you should. You don't want to do it too slowly either. You'll be sitting there all day. And again, you would record when the liquid first appears, the starting point, and the end point when the entire liquid solid is liquid. And you'll do this. Now, you would be using biphenyl, benzoic acid, and urea, and transenamic acid. Yes, there's a trans double bond there. I'll talk about that. Derivative of transenamic acid, why it's called that, and that's the common name, is found in cinnamon. But anyways, notice urea and transenamic acid have the same melting point, start and finish. And I would have told you in today's lab, because you wouldn't have this data, you would have to figure it out yourself, whether or not I'm lying to you, because you'd also do a 50-50 mixture. And in real life, if you had, you'd see, as you can see here, the melting point is lower and wider. Now, today's lab, if we had been face-to-face, to make it exciting, don't forget I wrote all these labs, I would have you do an unknown. Now, the unknown, first of all, you take a melting point. And then, if you notice in table 1, these are the literature values for the melting points you have done today, or would have done. And literature is someone like me who was a chemist who had measured these and published the values. And usually you can find more than one. And what I would be telling you is you're going to use the colligative effect to determine the unknown of compound A. Why? Well, at this point, I get creative and say the assistant state's attorney at Kane County needs the identity of A to convict a heinous criminal of a very dangerous crime. I'll let you fill in both of those, what crime. And so we have to know what is A. How do you do that? You use the colligative effect. You take the melting point and you get that number. You look at the table 1. Unknown A is one of those 4 compounds. Nothing else. You don't have to go anywhere else. Students get confused, go on the internet and look for it. No, it's in table 1. And then, based on your initial melting point, you'd say, well, I think it's this one. And you take a little equal amounts of the unknown and what you think it is, mix it together. And because of the colligative effect, if they're the same compounds, the melting point will not change. And you've now identified it. If it's different, your unknown, the one you think it is different, then colligative effect, wider, lower melting point. And since we're not going to have you do that at home, I gave you the data. Now, remember, in real life, your melting points are going to be a little lower than the literature value. So if you were in a lab right now, you'd get a melting point about 118 to 120. And if you look down here, you have a couple benzoic acid, and you could have said, well, I'll try also cinnamic acid, transenamic. And the melting point, when you mix the unknown with benzoic, you would have gotten 117 to 120. And if you mixed it with cinnamic acid, the unknown, you would have gotten 100 to 125. That will help you identify what is the unknown. Now, does everybody see here where it says identity of unknown compound? You have to write the name in there. And then for the lab, here are questions that you should do and answer. Now, you don't need to write 5 paragraphs. Most of my questions, 1 or 2 sentences, rarely 3, should suffice as an answer. And this is due next week. Now, let me open up one thing that I don't think I went through and I should do now. All right, here's the course syllabus, and all labs will be on Zoom. Each lab is going to be worth 11 points. Please don't hand them in late. I reserve the right to take off points. You'll lose 2 points for a late lab if it's more than 8 days after the lab. So this one, you have until realistically next Wednesday or Thursday to have it handed in. My labs, if you've been paying attention, you can also go back and watch the video of this, which I'll post later tonight or tomorrow morning, and answer the questions. Now, if you don't hand in a lab at all, you get 0 points. And I'll be honest with you, the way I grade, these are not hard points to get. Hand in the labs. I don't know why, but it seems like during the pandemic and now, students the hand-in rate or not handing in labs percentage is higher than when it's face-to-face, which hurts your grade. It's not that hard. If you have any questions with the lab, like anything else in this class, there's no such thing as a dumb question. Always feel free to ask. Come to my office hours or see me after a class. I've got some time. I don't have to run away. So anyways, you'll be handing in those labs. Each one is worth 11 points, and you have until next Thursday to hand it in. And then I'll grade it and post it, your score, out of a maximum of 11 points in D2L. If you ever have a question of why I graded a lab a certain way, always feel free to ask me. All right, like today, oh, it's the 1st of February, yay, whatever that means. And we just did the melting point. All right, any questions about the lab? If I look at the clock, that's about how long I'd normally take. Going once, looking at the chat, nope, twice. All right, again, this is due next Wednesday, and have it in at the latest Thursday. All right, let's get back to some chemistry. We're talking about alkenes. Let me just do one thing. And we're talking about addition of an acid to an alkene. All right, you see the whiteboard on there. You should see double bond, 2 lines between carbon. When you react it with HX, Remember, I can, or an organic chemist will write a reaction A plus B makes C, and we also write it this way. A plus B makes C, the product. Now, you break the pi bond, and one carbon of the double bond gets H, the other gets X. And it follows Markovnikov's rule. The carbon of the double bond with the most hydrogens gets the H, the other car gets the halogen X. And X in organic chemistry for this reaction is chlorine, bromine, or iodine, the halogens. Chlorine, HF, is really dangerous. And I've never seen it used for this reaction, maybe because of that. Now, if we look at this reaction, I'll do this, then I'm going to have you have some fun too. I share the fun. Question is, what's the organic compound products? And these are reactions organic chemists use to make compounds in your daily life that you use and you buy. All right, so how do we do this? Whenever you look at an organic molecule, look for what's different, what's not carbon, what's not hydrogen, what's not a carbon-carbon single bond should get your attention like this. That gets your attention. And, oh, look, it's a double bond. And as soon as I see that, and the rest is carbon, hydrogens, carbon-carbon single bonds, this is where the action is. Halogen and HCl, HX. Remember, X can be, in our case, it is chlorine, bromine, or iodine. You break the pi bond, one carbon gets H, the other X, and it follows Markovnikov's rule. The rich get richer, the poor get poorer. We're talking about hydrogens, or the carbon with the most hydrogens gets the hydrogen from HX, the other carbon double bond gets the halogen. So here are my two carbons. This has 2, this has 0. Which is the larger number? Isn't the math hard in my class? Hopefully all pick 2. Now listen carefully. Do you break carbon-carbon single bonds except for combustion in this class? No. So I have 4 carbons across, and I have 2 methyl groups, CH3. They're going to still be there. Now, here are my 2 carbons of the double bond. This has 2 hydrogens. Therefore, Markovnikov's rule tells me the hydrogen goes here, and the other carbon double bond gets the halogen. Halogen counts as a bond. Remember, there's 4 bonds to carbon, so I can put in the rest of the hydrogens. Remember, it's your solemn responsibility to correct me if I make a mistake. And there you go. And this is the hydrogen attached to that carbon. And that's Markovnikov's rule. That's your turn. Again, give the organic compounds for the following. While you're doing that, I'm going to check my cell phone, see if I got any text messages from my dealer. And the good news is no. There'd been an expensive repair, I probably would have gotten a call by now. Well, I think everybody's done. So I'm going to do it. And if we look at this molecule, look for what's different. What's not a carbon-carbon single bond? Oh, a double bond. I'm reacting with HBr. Remember, a halogen bromine is X, HX, and X can be chlorine, in our case, bromine, or iodine. And you break the pi bond. Remember, this is one pi bond and one sigma or single bond. And I broke the pi bond. That's why there's only one line between these two carbons. And one gets H, the other gets X. And it follows Markovnikov's rule. The carbon with the most hydrogen gets the hydrogen, the other gets the halogen. Well, here's my double bond. This has one hydrogen. This has two. Which is greater? Hopefully you pick 2. You break carbon-carbon single bonds? No. I have 4 plus a methyl. I better end up with 4 plus a methyl. Here are my 2 bonds, carbons, double bond. The hydrogen goes to this carbon because it has more hydrogens. The halogen, which is bromine, goes here. And now I can put in my hydrogens. And remember, there's 4 bonds to carbon. And I'm done. And that's how you do. Oh, let's do another one. And I'll do this one. And then I'll let you have fun with one. All right. We look at that. We say, oh, what's different? I got a ring, but that's just carbon-carbon single bonds, but I have a double bond. Reacting it with HI. Iodine is a halogen. Remember, X can be chlorine, bromine, or iodine. 1 pi bond, double bond, 1 sigma bond. Break the pi bond. 1 carbon gets H, the other gets X. And it follows Markovnikov's rule. So I look at the 2 carbons right here, the double bond, and I say, all right, which the one with more hydrogens? And I look and say, oh no, I don't see any hydrogens. Oh, well, wait, there are 4 bonds to carbon. And if I notice this top carbon right here, it has 1, 2, 3, 4. So 4 minus 4 means this top carbon has 0 hydrogens. If I look at this carbon, it has 1, 2, 3. 4 minus 3, remember there's always 4 bonds to carbon. And 4 minus 3 is 1 hydrogen. And that's what you have to do with the ring. And now I can go ahead and say, which carbon has more hydrogens? The bottom one. The hydrogen will go there. The top carbon will get the halogen. Do you break carbon-carbon single bonds? No. Have my ring and my methyl group. I broke the pi bond between these 2 carbons. There's only 1 bond. And this top carbon gets the halogen, iodine, and I don't have to show anything on the bottom. Why? Because if we look at this carbon, has 1, 2 bonds. 4 minus 2, because there's always 4 bonds to carbon, means there's 2 hydrogens. You started with 1, now there's 2, so you actually did add this hydrogen there. You just don't show it. So when you have a ring, you have to count bonds. Remember, there's 4 bonds to carbon, and then determine which carbon has the most hydrogens, and that gets the hydrogen. All right, your turn. Give the organic product or product for the following. And you'll learn later in the semester, it turns out it's very useful to be able to convert something with a double bond to something with an halogen, to use it to make something else, which allows you to make other things. Think of it like a chess game. You're learning the various moves of the players. In a chess game, you put a bunch of them together to win the game. Checkmate. I haven't played chess in a long time. I used to play it all the time with my father until by the time I was 15, I started beating him all the time and he got upset and stopped playing. I guess if you lose all the time, that's not fun. All right. And it looks like everybody's done, so I should get to work. If I look at this ring, I look for what's different, what's not carbon, what's not hydrogen, what's not a carbon-carbon single bond, and I see a double bond. The rest are things that just are going to come along for the ride. I'm reacting with HCl. Chlorine is a halogen, which we show by X. Remember, X in our case is chlorine, and it could have been bromine or iodine. And you break the pi bond. Remember, there's 1 pi bond, 1 sigma bond, and 1 carbon gets H, and the other gets X. And with that, it follows Markovnikov's rule, M's rule. The carbon of the double bond with the most hydrogens gets the hydrogen, the other gets the halogen. And as I still remember, the rich get richer and the poor get poorer. Now, if we look at a ring, we have to count bonds. This carbon has 4 bonds to it. And there's always 4 bonds to carbon, so it has 0 hydrogens. This carbon has 3 bonds to it. 4 minus 3 is 1. Do you break carbon-carbon single bonds? No. So I'm still going to have my ring and have my methyl group here, CH3, my ethyl group, CH2, CH3. The top carbon will get the hydrogen, which you don't show. If you want to, go right ahead, but don't. And the bottom will get the chlorine, which I can write like this. And you could have also, for this class, written it that way. And that's how you do it. Oh, we're getting some good chemistry now. And I'm happy if you haven't figured that out. And that's reaction of an acid HX with a double bond. Let's move on. Now, let's talk about addition of water, which is called hydration, of an alkene double bond. Here's the reaction I have on here. I'll show you a better way to denote that reaction. If you have any double bond, you react it with an acid. Now, H plus is the general way of an acid. Excuse me, I got to answer that. Hello? I apologize for the delay. It's going to cost me some more. I knew I probably needed a new battery and they got to put in a new air filter, but I've been using this dealership for a long time now. So guess what? I trust them. And my car's old enough and running well enough that I know they'll do the good thing. All right. Well, what that means is let's finish up this, take a break, and then I can continue on. All right. We're talking about reacting water and an acid to a double bond. Now, H plus in organic chemistry means an acid. And there are many acids. Remember, an acid is a proton donor. I'll never ask that. But whenever you see H plus, that means you're adding an acid. And a lot of times the acid we'll use is sulfuric. Now, there are other organic acids, which I won't teach in this class, that I've actually personally used, like methane sulfonic acid and toluene sulfonic acid, but they all donate a proton, and that's what we show. Now, here I have water, H2O. Now, let's look at water and think about it in a different way. Think of water as H and OH. Now, OH alone is called a hydroxyl group. And I'll never ask on a test what's a hydroxyl group, but I will use that term. And remember, we have one pi bond and one sigma bond. Now, the acid is a catalyst. And a catalyst is something that makes a reaction go quicker, but is not consumed. So what really happens is when you break the pi bond from the water, one carbon double bond gets H, the other gets the hydroxyl group OH. And guess what? This follows Markovnikov's rule. The carbon of the double bond that has the most hydrogen gets the hydrogen from water. The other carbon gets the hydroxyl group from water. And when you put an OH hydroxyl group on a carbon, you'll learn later in the semester, that's called an alcohol. If I look at the clock, I think we went, because my phone call a little longer than I wanted to. Let's take a 5-minute break, come back by 1 o'clock, 2 o'clock, the other, come back in 5 minutes, and we'll continue on. See you in 5. time to get going. And again, thank you for your understanding for that important phone call I had to take. My car's in good hands, luckily, with the dealership, even though it's going to cost me more than I expected, but I also knew that. But, okay, I have the money. That's one of the things my parents taught me. Time for a personal lesson. All the years I've had credit cards, only once, decades ago, because I was first starting out, did I ever not pay the balance on the month it was due. My credit cards, if I don't have the money to cover it before I charge it, I don't. But that's also because I save a lot too, always have. Ooh, word to the wise, I did it, you should. Once you get working, set up some IRAs or other types of annuities where every month, even put in a little, by the time you get to my age, it helps. I'm in a good position, unlike many people my age, because I did that. And also I'm still working, but even if I wasn't, I'd still be in a good position. All right, let's get back to organic chemistry. We're talking about the reaction of acid and water hydration of a carbon-carbon double bond. And this is a way of making a molecule, you'll learn later, a functional group called an alcohol. And we'll learn alcohols are more than what you think of an alcohol, which is the good stuff you drink on the weekend or wherever, like vodka. Dr. White likes his vodka. Ooh, public service announcement, real quick one. If you're a vodka drinker, I like Grey Goose and Absolute, and also Genever, Neue Genever, which is Dutch vodka. The Costco French vodka is almost identical to Grey Goose and Absolute, and it's a lot cheaper. All right, let's get to work. And the question is, give the organic product or products to the following. And by doing this, we make molecules, we organic chemists, that are used in your daily life. Maybe not this one, but just to give you an example. I'll do this one, and you know I'm going to share the fun. So how do you do this? You look for what's different. What's not a carbon single bond or a carbon or hydrogen atom should get your attention. Ooh, a double bond. And if I look right here, what am I reacting with? Acid, catalyst, that's what the H plus is, and water. Remember, think of for this reaction, water is HOH. And you break the pi bond. Remember, a double bond has one pi bond, one sigma bond, and one carbon in double bond gets the hydrogen from the water. The other carbon gets the hydroxyl group OH. And it follows Markovnikov's rule. The carbon with the most hydrogens double bond gets the hydrogen. The other carbon gets the hydroxyl group OH. And if we look at our double bond, now we got to do the hard part with math. This has one hydrogen. This has 0. Which is the greater number? Hopefully you picked 1. So do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4, 5 across, plus this methyl group, which I just put in the wrong place. Don't look. And which are my 2 carbons of the double bond? These 2. And my structure here, notice I broke the pi bond. This carbon has more hydrogens, we'll get the hydrogen. The other carbon will get the hydroxyl group. If there was room instead of a carbon down there, I'd put that underneath, but there isn't. And I know there are 4 bonds to carbon. OH counts as a 1 bond. And that's how you do it. Again, you break the pi bond, the hydrogen goes to the carbon with the most hydrogens, and the hydroxyl group OH goes to the other carbon. And we've taken a double bond and make it into an alcohol. Now, it turns out in real life, you can go out to Mother Nature and other places and find certain molecules with functional groups that you convert into others. In every company I've worked for, we've done that. You know, later on, I'll tell you, I've worked for two companies that started out with vegetable oil or animal fats and made them into many things such as soap or fabric softener or other chemicals. All right, your turn. And there you go. Give the organic count product or products for the following reaction, 3 points each. And we're doing some really serious organic chemistry right now. And it's fun. Don't forget I'm biased. I'm a synthetic organic chemist. And don't forget, if you're done, do the poll, please. All right, I think everybody's done. So my turn. If we look at this molecule, look for what's different, what's not carbon, what's not hydrogen, what's not a carbon-carbon single bond. Oh, by the way, in about a month or two, hopefully you won't have nightmares hearing me say that. But it's the most important thing I always do. I say a double bond. And when I look at a molecule, I look for that instinctively. I've been doing it long enough. And we're reacting with acid and water. Remember, H+. This means an acid catalyst. And water, H2O. And think of water as HOH. Remember, double bond has one pi bond, one sigma bond. And you break the pi bond, one carbon gets H, the other gets the hydroxyl group OH, and it follows Markovnikov's rule. And that is the carbon double bond that has the most hydrogens gets the hydrogen, the other carbon gets the hydroxyl group OH. Now we have to look at both carbons in a double bond, and this carbon has two hydrogens, this has one. You have to use your high-level math skills, which is the larger number, and time's up. Hopefully I'll pick 2. So the hydrogen will go to this carbon, the hydroxyl group will go to the other of the double bond. Do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4, 5 across. I better end up with 5 carbons. And I have 2 methyl groups. They come along too. Here are my 2 carbons of the double bond. I've broken the pi bond. This gets a hydrogen. This gets the hydroxyl group. I know there are 4 bonds. Yes, 4 bonds to carbon. So OH counts as 1 bond. And that's how you do it. Again, this follows Markovnikov's rule. The carbon of the double bond with the most hydrogens gets the hydrogen, and the other carbon gets the hydrox group OH. Ooh, this is fun. We got to do another one. And here's another one for you to have fun with. Get the organic product or products for the following, 3 points each. And again, please be patient. I try and give everybody time to finish. And I do. All right, I think everybody's finished. So it's my turn. And how do you do this? You look for what's different, what's not a carbon-carbon single bond or carbon-hydrogen atom. Ooh, a double bond. The rest of those aren't going to react with just about anything. So I have a double bond reacting with acid catalyst. Remember, H plus means acid catalyst. And water, H2O. Remember, water is HOH. And you break the pi bond. Remember, double bond has 1 pi bond, 1 sigma bond. And 1 carbon gets H, the other gets the hydroxyl group OH, and it follows Markovnikov's rule. The carbon with the most hydrogen gets the hydrogen, and the other carbon gets the hydroxyl group. Remember, the rich get richer and the poor get poorer. Do you break carbon-carbon single bonds? No. So I have a 5-membered ring. I have my isopropyl group. Hopefully you've learned your alkyl group names. And I have my 2 oh, it's a ring. Did I tell you students hate rings, but Dr. White, Mother Nature, loves rings, and I do. In fact, my PhD thesis dealt with making a very complex ring system, which I really won't talk about this semester. Sad, but true. All right. Well, for Markovnikov's rule, we have to figure out how many carbons are in a bond. If we look at this bond right here, 1, 2, 3, 4. 4 bonds to that. There should be 4 bonds to carbon. 4 minus 4 is 0. If we look at this carbon, there's 1, 2, 3 bonds. There should be 4 bonds to carbon. 4 minus 4 is 1. And which one of these numbers is larger? Hopefully you picked 1. And now we know that the hydrogen goes to carbon 1, carbon with the most hydrogens, and the hydroxyl group goes here. And you could have also written it this way. Either one would be correct on the test. And that's how you do addition of water, also known as hydration of a double bond. Hydration means adding water. If you were working in a hospital and they brought someone in and said, this person's dehydrated, that means they don't have enough water. Hopefully that never happens. All right, time to move on. Let's get to triple bonds. All right, now triple bond, remember that's 3 lines between 2 carbons, is an acyclic unsaturated hydrocarbon with more than 1 triple bond, 1 or more. In this class, we're going to stick to 1. And the bond is linear, which means you don't have to worry about cis or trans. Now, this has now 2 pi bonds and 1 sigma bond, where double bond only had 1 pi bond and 1 sigma bond. And the IUPAC names are similar to alkenes, except you don't use the EN ending, you use the YN ending. And there's no cis-trans isomerism because it's straight. It's not got the 120 bond angle. So let's look at nomenclature of alkynes. And the question would be, give the IUPAC name for the following. And how do you do that? Well, like double bond, you find the longest chain with both carbons of the double bond. But before I do that, let's look at the structure. Look at the 2 carbons of the double bond. There's 4 bonds to carbon. The triple bond counts as 3 bonds plus this one. That means each of these carbons already has 4 bonds, which is why there are no hydrogens. So you find the longest chain, 1, 2, 3, 4, 5, or 5. You name that as pentane. Drop the ANE ending. And remember, drop the ANE ending, triple bond, YNE, pentyne. And then you find, like you did for double bond, what carbon of the triple bond is closest to the end of a chain. You number it in the direction to give it the lowest numbers. If I started the other way, it would be 3. Here, the lowest number is 2. So it's 2 pentyne. You cannot have cis or trans in a triple bond, so we don't have to use that. And notice, once I say 2 pentyne, this is all spoken of. Oh, look, it's your old friend, the methyl group. And it's on carbon 4. So that would be 4-methyl 2-pentyne. Now, I was looking earlier today and I found, to my surprise, because I was where people recently in the last decade or so, I haven't looked in a long time, were able to make a triple bond in a ring, but it's so unusual. I've never seen it in the chemical industry used for anything. So we're not going to cover it in rings. This doesn't happen in all intents and purposes. So what would be the IUPAC name for this molecule? Your turn. Remember, YNE is used for triple bonds. And when I was an undergrad, part of my undergraduate research my senior year dealt with triple bonds. I think just about every functional group I'll teach you this semester, I've worked with a lot. Isn't it nice to have an instructor who knows his organic chemistry and has actually used it? You don't have to answer that. All right, everybody's done, so I should get to work. Look for what's different. Ooh, a triple bond. What's not carbon? What's not hydrogen? What's not a carbon-carbon single bond? Ooh, it's not working again. There. You get your attention like that. Triple bond. How many carbons longest chain with both carbons triple bond? 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, 6. 6 is longer than 5. 6 is hexane. Remember, drop the ANE and replace it with YNE, hexine. And good news, I don't give enunciation quizzes. I heard one instructor years ago did. What? Anyways, so where's the double bond, triple bond, I mean? 1, 2, it starts at carbon 1, 1 hexine. If that's 1, this is 2, this is 3. Oh, it's your old friend, the methyl group. Because as soon as I say 1 hexine, that's all spoken for. And the methyl group is on carbon 4 again. Wow. So that's 4-methyl 1 hexine. Now, one thing I should point out, let's do a simple, or I'll do the one above. Notice right here, the hydrogen, that's called left justified, with carbon at the left, carbon, either CH3 or triple bond, double bond. You can have it also left or right justified. And both are the same. My software likes to do it this way. I've got to override it to do it that way. Usually with CH3, I'll do it that way. With triple bonds, I can do it both. And in real life, other chemists to do it too. Oh, let's do another one. And here's another one. I just think that's B, whatever. 3 points, give the IUPAC name for the following. And don't forget, I mentioned earlier, and you should have gotten an email, test number two, test number one, the new date will be February 15th, that Wednesday, as opposed to next Wednesday. This way I don't have to rush. I'd have to rush real quick, cut down on examples. That's not right. That doesn't help you learn. And for those of you with your webcam on, thank you. For those of you who showed up with your webcam off, thank you. All right. Before I do this, time for public service announcement from Dr. White. Did you happen to think of alkanes when you drove by a gas station? Remember, organic chemistry is all around you. I stole that from SpongeBob. It won't hurt for you to think about organic chemistry when you're not in my lecture or class. Remember, gasoline, about half the weight are alkanes. There are other things we'll talk about later in the semester. And did you think about double bonds when you looked at a carrot or tomato? I've got the whole semester to work on you guys. All right, let's go back to this. What's different? What's not a carbon-carbon single bond or a carbon-hydrogen? A triple bond. We're doing nomenclature. How many carbons in the longest chain with both carbons triple bond? 1, 2, 3, 4, 5, 5, 5. So that's pentane. Drop the ANE at the end of pentane, and you replace it with YNE, pentyne. Now, you number it in such a way that both carbons of the triple bond have the lowest numbers. If I start this way, it would be 2-pentyne. Look out, I'm going Technicolor on you. The other way would be 3-pentyne, which is lower too, which is why that's the way I'm numbering. Let me get rid of the red numbers. And if this carbon is 2, I have, as soon as I say 2-pentyne, those are spoken for. And carbon 4, I have not 1, but 2 methyl groups. Remember, we use di for 2 groups. And tri for 3 groups. So there are 2 methyls, so that's dimethyl. Now, as soon as you see di, you need 2 numbers, even if they're on the same carbon. I did this example to remind you that. So that should be 4,4-dimethyl 2-pentyne. If you just put down 4-methyl-dimethyl, I take off points because it's wrong. And that's how you do it. Now, you'll see on test 1, 2, and 3, and the final, not so much test 4, there's actually at that one too, but not as much. But there are two types of nomenclature questions or naming. Remember, nomenclature is a fancy way of saying naming. The first one is give the IUPAC name for the following. And let's look at this one, 3-methyl-1-octyne. How do you decode it? I'll do this one, then I'll let you have some fun too. You start from the right and move left. Y-any ending means triple bond. If that were A-N-E octane, hopefully by now you've learned that table, that's 8 carbons. And where is the lead carbon of the triple bond? Carbon 1. Most of you will do it this way. You could have also started from this side, but most of you won't. Carbon 1, then I have a methyl group, CH3, on carbon 3. And I know there are 4 bonds to carbon, so I can put in my hydrogens. And now I have triple bond, 8 carbons, octyne. It's on carbon 1, the lead carbon is the first carbon triple bond, and carbon 3, I have my methyl group. And that's how you do it. And why don't you draw the structure for 4-ethyl-2-decyne? 4-ethyl-2-decyne. And it looks like everybody's done. So how do you decode this? Know what to draw? You start from the right and move left. YNE ending tells you you have a triple bond. If it was ANE, 10 carbons, well, I better get to work. 10 carbons. Where does the triple bond start? Carbon 2. And then on carbon 4, there's an ethyl group, 2 carbons. And now I know there are 4 bonds to carbon. Does it look like this is in 3D coming right at you? Oh, that was an awful joke, sorry. And there we go. 4 ethyl, 2 decyne. And remember, the longest chain has 10 carbons, decane. And YNE tells you it's a triple bond. Oh, let's do one more. And that would be 4,5-dimethyl 1-9. And remember, tonight, I will be having my office hour from 6 to 7:15 on Zoom. If you have any questions, need any help, or if you just want to stop by and say hello to Dr. White, feel free to. Now, if you can't make it to my office hours and you really need help, email me and I'll see if we can set up a Zoom meeting when you and I are both available. Because I want everybody to do good. All right, let's do this. How do you decode this to know what to draw? You start from the right, move left. YNE, excuse me, getting all choked up over triple bonds. If that were ANE, nonane, that's 9 carbons. Oh, excuse me, got a feather in my throat. No, I didn't eat a bird. Oh no, that was a bad one. All right, where's the triple bond? Carbon 1. And then methyl, I know that's CH3, di. Wait a second. Someone was nice enough to write di means 2 groups, tri means 3. Well, I've got dimethyl, and where are they? It's carbon 1, 2, 3, 4, 5. One's on 4, one's on 5. I know there's 4 bonds to carbon. Yes, 4. So I can put in my hydrogens because I know how to count. And there you go. 4, 5 dimethyl, 2 methyl groups on carbon 4 and 5, 1, no 9, triple bond, longest chain, 9 carbons. And that's how you do nomenclature of triple bonds. All right, let's move on to reactions of triple bonds. Now, because I like to spend more time on things that you probably will use more in your real life, we're just going to do 2 of them. There are a lot more reactions I could do, but I'm only going to do 2 because I'd rather spend more time later in the semester on things that are more important to you, like things you use in your daily life, like fats and oils, carbohydrates, and proteins, which we'll cover later in the semester. But here I have any triple bond. Remember, R is like in math, X and Y. That means something with carbons and hydrogens. Now, did I tell you how lazy organic chemists are? We are. We don't want to balance chemical equations if we don't have to, especially if you're not calculating charge weights. Well, if I have a triple bond, I have 2 pi bonds and 1 sigma bond. And when I add hydrogen plus a catalyst, where the catalyst, just like with a double bond, can be platinum, palladium, or nickel, I break each pi bond, and each carbon of the triple bond gets not 1, but 2 hydrogens. For each pi bond, it gets a hydrogen. 2 pi bonds gets 2. Well, I've got to balance that. No, I'm an organic chemist who's lazy. So if you notice, I have bracket, the letter X, the letter S, close bracket. What that means in organic chemistry is the term excess. Isn't that cute? Excess. And that means I have all the hydrogen in the world to react with anything that hydrogen can react with. In this case, the 2 pi bonds. And that's hydration of an alkyne. Y-N-E-N-D, triple bond. And if we look at the following, the question would be, give the organic products for the following reaction. So how do you do that? You look for what's different, what's not carbon, what's not hydrogen, or carbon-carbon single bond, get your attention like that. Ooh, a triple bond. And that got my attention. I'm reacting with hydrogen, and notice excess. That means I have all the hydrogen in the world, anything that can react with hydrogen, and a platinum catalyst. Remember, the catalyst can be nickel, in our case, platinum, or palladium. And you break the 2 pi bonds. Remember, triple bond has 2 pi bonds and 1 sigma bond. It's something you should know. And each carbon of the triple bond for each pi bond gets a hydrogen. 2 pi bonds, 2 hydrogens. And therefore, do you break carbon-carbon single bonds? No. So I start with 4 carbons, I better end up Notice these two carbons right here. I broke the pi bonds, and each one gets 2 hydrogens. And I know there are 4 bonds to carbon. And I can write it that way. Now, another way you can write it, but you don't have to. Notice this carbon has 2 hydrogens. This has 3. I could write it this way. This is easier for you. It's less work on a test. Oh, that reminds me. I forgot to do that. Hopefully by tomorrow morning, I'll send out an email with a private link. Please don't share it with anybody else, for a video I posted on YouTube. It's private, so you can't look at it as a general public, on the presentation on test anxiety, which will allow you to look at that. I'll delete it in about 4 weeks, right after test number 1. Actually, more than after test number 1. All right, well, that's how you do it. And let me have you try it. Your turn. Give the organic product or products to the following reaction. Now I'm going to go a little past where we normally cut off because we're going to end early today. We do that normally on Wednesdays. I want to get to a certain end point. You'll see why. And if you want to get a head start, I would say the way it looks now, next Wednesday, I'll probably go through the alkenes, alkynes problem set. I'll finish up early Monday beginning. So you can start on the alkene part of that problem set now, this weekend. Give you something fun to do. Oh, you can give me that. What are you talking about fun? Well, remember, I'm an organic chemist. All right, looks like everybody's done. My turn. If we look at this molecule and say what's different, what's not carbon, what's not a hydrogen, what's not a carbon-carbon single bond, I see a triple bond. And if I take my triple bond, that's the only thing that's going to react. What am I reacting with? Hydrogen, but notice XS means I have all the hydrogen in the world that hydrogen will react with in the presence of a catalyst. Remember, your catalysts are nickel, platinum, or in our case, palladium. And you break, remember, this has 2 pi bonds. This has also sigma, you don't break. And you break for each pi bond, each carbon gets a hydrogen. 2 pi bonds, each carbon gets 2 hydrogens. Do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4, 5, 6 across. I better end up with 6 across. Here are my 2 carbons of the triple bond. Each one gets a hydrogen. And I know there are 4 bonds to carbon, so I can put in my hydrogens. Oh, let's have fun. And the question is, give the organic product or products are the following. 3 points each. One of the things on my test you'll see, I try and keep points for problems small, as opposed to putting a few that are a lot of points, because that helps students do better, which I like to see. Also, you'll find when you take my test, you'll have more than enough time, even if we were face-to-face. You've done the practice problems. My test should be a breeze. I don't know about a breeze, but you should do well. Did I tell you historically, face-to-face and on Zoom, I usually see about 60 to 5%, 70 students, listen carefully, who earn A's. And usually the bulk of the students, 95% are A's and B's. All right, let's send out the poll. Everybody's done. We look here, look for what's different. I'm going to say that a lot, but when I look at that molecule, I scan it, I say, what's not carbon, what's not hydrogen, what's not a carbon-carbon single bond? That got my attention, triple bond. I'm reacting with hydrogen excess, which means I have all the hydrogen in the world with anything that hydrogen will react with, and I have a catalyst, nickel. Remember, your catalyst can be nickel, platinum, or palladium. I don't know if you've seen news recently where in certain parts of the city of Chicago, they're once again stealing catalytic converters in cars. And those are a mixture of platinum and palladium, which is a lot of money. In fact, I thought I heard the other day that at a police station in Chicago, some of the police vans, they stole the catalytic converters. That surprised me. You'd think they'd know better, or at least protect their own vehicles better. Now, remember, triple bond has 2 pi bonds, 1 sigma. You break pi bonds very easily. For each pi bond, each carbon of the triple bond gets a hydrogen, two hydrogens. Do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4, 5 across, plus 2 methyl groups. And it's important where you place the methyl groups. Here are my 2 carbons of the triple bond. I broke the 2 pi bonds. That's why there's only 1 line. Each one gets a hydrogen. And I know there are 4 bonds to carbon. And if I make a mistake, please correct me. And there you go. And that's the molecule you would make. If I look at the clock, it's time to stop. Normally, we would have gone 50 minutes, then I do a half hour. I went a little longer today. I wanted to get on track. And with that, I'm done for today, unless you come to my office hour tonight. So I'm going to wish you a good rest of the day, rest of the weekend. I'll either see you tonight if you come to my office hour, or I'll see you on Monday. And with that, I'll say, remember, this means go in health in Yiddish, which is a mixture of Hebrew and German. My grandmother used to say this all the time. She's a great lady, Grandma Greenman, Bessie Greenman. But anyway, she used to always say, she didn't do this, but I'll do it. Gang gesund. I'll see you on Monday or tonight. Remember, I stole this from Granny of the Beverly Hillbillies. Look on YouTube if you don't know what that means. Bye now.